So according to our schedule tonight, we should be looking into microcontrollers architecture, microcontrollers architecture to understand computer architectures, the two type of architecture, the von Neumann's and hybrid architectures, and why hybrid architecture dominates computer systems and microcontroller world. Two-stage pipelining, concept of latency, throughput, and frequency. Introductions to datasheet and importance of datasheets, evaluating PIC 16 F8771 ATMEGA 32 architectures. Alright, good evening everybody. I believe my intention is to make this class as fast as possible, so that some of us that we have some other engagement to will be able to get it done. But of course, we are spending more than 1 hour still, but I'll make it as much as details as I could. Alright, I welcome everybody to this class. Thank you, Uncle Peace, for getting us a link. Peace is the one that generates this link for us, so that subsequent time we won't be thrown out of Google Meets like that. So, alright. So, what is computer architecture? Computer architecture is about the way computer tries to evaluate, try to analyze, try to carry out its processes. What process does it use to carry out this activity? All right. Fundamentally, there are two processes. Or let me say three processes that any computer system try to follow to evaluate, to carry out its instructions. There are two processes. So let me stop this and share my slide. I think that will be much more better than what I'm sharing. When we get to data sheet, then I will share the data sheet. So slide this and this. Okay. Am I showing? Is my screen showing? Is my slide showing?
Yeah.
Alright. So I believe we should be here today. Yeah, we should be here today. Alright. So there are three fundamental processes that any microcontrollers, any computer system try to execute programs, try to execute instructions. Number one thing is that in our previous class, I talked about computer being essentially a secretary, and I said that this secretary most times has two kind of memories. One called the program memories, which is the memory of his brain at which you train him on what to do, and the registers, which is the working memories, where it keeps the file, where it keeps all the informations. So what really happens is that this memory computer system try to first of all fetch instructions of what to be done from the memory here. Then the CPU, which is the secretary, which is actually the processor, now evaluate, decode the instructions, process the instructions, and knows what to be done to the memory, then write back the results into the memory. So first of all, you fetch the instructions from the memory. Then when you fetch the instruction from the memory, you decode it, you interpret it, what you want us to do basically as a result of that instructions. Then the next thing you do is that you write back the instructions to the memory. Let's take a very simple example so that I will evaluate this. Now let's say I'm writing a program that take readings of temperature from LM35. LM35 is a temperature sensor. It's an analog temperature sensor. It has a 3-pin. One faces input and the other one output. When it takes this output from this analog is being stored in a memory, and the name of that memory location is called address. So let me just type the name of that memory. It's just for the purpose of this class. When we get to ADC, we'll look into that in details, but I want to just type the name of that memory locations so that for us, for the purpose of this class. So for if it is in If we are talking about PIC microcontroller now, we are looking at two microcontrollers in this class. So the result is stored in if it is PIC microcontroller, this is the name of the two registers, address H and address L. Address stands from analog to digital conversion result registers. Higher level is 8-bit and lower level is also 8-bit. That's the name of the register at which the moment you do the ADC conversions, the result of that ADC conversions, whether it is 10, whether it's 100, whether it's 150 degree, is being stored at that in these memory locations. Why if it is in what's it called? What's the name of this one now? ATMEGA 32, the result register is stored in the name of this is the two name of the registers at which it is being stored into. So that's the memory locations where these informations of the temperature will be stored. You understand? So what CPU does is that CPU fetch this value from these memory locations and evaluate it. Meanwhile, the number is not going to be in this value at which you look at it now. It's going to be something in 1000. These registers are actually like this. They are all 8-bit, which is one of the things we are going to be looking at today. So now, based on that, my simple explanations now. So the CPU now has an instruction that says, if this information is greater than, let's say, 30. For example, what is 30? If I want to represent 30 now, that should be 0, 0, 0, 0. Or let's take 8, for example. If the value is going to be 8, then I expect this to be in my memory. This is 8 now. Now, if the value of the temperature is greater than 8, do something to maybe to turn off a light and to turn on a light. Of course, you can now be looking at the general purpose register. For example, you are looking at the general purpose register. For example, of course, we can look at DDRA. This is port A register in ATMEGA. You understand? Why in port A registers in ATMEGA? Why in this is in PIC? DDRA is in ATMEGA. So we'll be looking at those things. So what CPU does is it decodes information. You decide whether to write 1 0 0 0 0. That means you turn on a particular output as a result of what you saw there. You understand? Then or you turn off a particular output. So basically what happens here is that the CPU fetch informations of the ADC conversion unit, the results that was stored in the memory, evaluate what the instruction says should be done, then send back the results of what to be written into the memory. Now let me tell you something that is highly very interesting to me in my study of embedded systems and microcontrollers as a whole. Now this is what I come to realize, that even the 1 and 0s that you saw here, please, I just don't want you to forget this analogy I want to explain. Now, even the 1 and 0 that you saw stored here was not being generated by your microcontroller. It wasn't being generated by your microcontroller. You are the one that gave the microcontroller this 1 and 0. And that 1 and 0 is your VCC and your ground. So that means your microcontroller has a bank of 1 and has a bank of 0. Has a bank of 1 and has a bank of 0. Once we get to some certain part of this microcontrollers and our embedded system knowledge, I will tell you that you can have I, that is on stage, you can have 0, that is low stage, and you can have X, that is indeterminate state. Indeterminate state. So this 3 states is possible for a microcontroller to be. So a high state, a low state, or an indeterminate state. As an embedded system engineer, you want to try your possible best to ensure that you are not in indeterminate state. So what am I trying to say is that whether to write 1 or 0 into a particular location is a function of your. So what the processor does is that when it finishes the analysis, you just pick the bank of 1 or bank of 0 where you give it to him, which is the 1 or the VCC and the ground, and decide to write it back to the memory. And that is Fundamentally, these three processes is what every CPU undergo. Now, what is architecture? How they undergo this process, the ways at which each of them undergo this process is what we mean by architecture. So now some microprocessor is designed to be more faster than the other because of their architecture. You understand now? Now, if we split this much more better, we'll have discovered that these memory locations are two: the data memory and the program memory. Remember, the instructions was being fed in from a known memory called data memory. So if I'm to redraw this particular stuff now, let me see if I could do it fast. I will have said that first there's a data memory that feeds in instructions into the CPU. The CPU decodes it, then updates there's a program memory that feeds in instructions to the CPU. The CPU then updates the instructions and writes to the data memory. Now that means you need two lines generally that have to be connected to your CPU. One, the data memory, and the next one is the program memory. One, the data memory, and the next one, the program memory. Now, there are two major architecture that is reigning in the world. That leads us to, there are two basic architecture that is reigning in the world, where the two ways that the microcontroller is being executed their process in the world. One is using von Neumann architecture, and the other one is using Harvard architecture. Most microcontrollers you find today are actually using Harvard architecture. In von Neumann, you use the same data bus. What is data bus? A data line, a communication line. You understand now? It's basically 8 wires. If you are using 8 bits, it's basically 8 wires to send instructions, to send memory, to send values, to access the memory by the CPU. You use 8 wires. So if it is in von Neumann's architecture, this 8 wire is being shared by the data memory and the program memory. So what does it mean is that at the same time you can both fetch, you cannot fetch instructions and execute instructions at the same time. I don't know if I am so clear at this junction. So in von Neumann architecture, you have the same 8 wires that connect your data memory to your CPU. It's the same 8 wire that connects your CPU to your program memory. Thereby, if you are, so when you are fetching instructions, that means you are in fetching stage, you are fetching instructions, what to be done from the program memory. You cannot be writing to the data memory at the same time. So you have to first of all fetch instructions. Then once you finish fetching instructions, decode the instructions, understand it, then knows the register to work on, then write out execute the instructions now. So in that place, you have to do that step by step. But in Harvard architecture, as you are seeing on the screen currently now, uses 2 data buses. So one for the memory, the program memory, the other one for the data memory. So at the same time, you can both fetch instructions and you can both execute instructions. 2 memory locations for storing programs and for storing data. Then 2 separate buses. Sorry, this is buses, not bases. This typographical error. 2 separate buses for accessing those memory locations. Now, what is the end effect of this? Is that to the effect that this Harvard architecture tends to be much more faster for execution. If I am clear here, please, I just need a feedback. If there is no any challenge at this junction, I just need a feedback from you and from Peace that we are good to go. So I just explained 2 common architectures that you find around: the von Neumann architectures and the Harvard architecture. And the process at which CPU executes instructions. First, you fetch the instructions from the program memory, then decode the instructions, then process the instructions, then write the output to a microcontroller. Hello?
Yeah, I guess it was kind of the normal education you were talking about. Can you spell it so I can get
Okay,
the
okay, so that anybody that want to look into it, okay, I'm going to do that. So this is von Neumann. I want to believe this is von Neumann. Let me also confirm the spelling here, so that from okay, Newman, I think I get it. From Newman architecture. So this phoneme architecture, so that's the spelling. You can just go through it. It uses the same memory for both program memories and data memories. Then you use one data buses to share information from them. Then that means the system is going to be slow. Then what is the advantage of phoneme architecture? The advantage is that it's less costly. Like it's of course it's at a reduced cost compared to architecture, because you won't have to have two separate memories, then you won't have to have two separate data buses, but speed was sacrificed for cost. Do you understand? And in Harvard architecture, cost was satisfied for speed, and that's the two major difference between them. So if that is good, if we understand that, then that will take me to a concept called pipeline. Then what will you do for me if I understand architecture with my microcontroller? What will you do for me? I put two reasons here. First, it will make me to understand how my processor executes executes instructions, how it exchange data. I will begin to understand what happens within the microcontroller itself. Then that will be able to also help me to be able to write a better code, because I will know what I can take advantage of and I will know what I cannot take advantage of. Let me put that into a perspective, like an example, so that we can get what I'm trying to say. Now, if you're writing on Arduino IDE, most likely you'll be seeing something like this. So you'll be seeing something like this. Just write an output. I'm just writing a typical code just on my screen now. So I want to share this. So if you write something like this on Arduino IDE, like you are writing with Arduino IDE, I believe my screen is also seen. So you write digital write let print I. What this instruction is doing is that it's going to turn on a particular GPI open, but in MPLAB IDE, and you write something like this. Write something like this. What is the difference between them? Now these ones, now at one instruction cycle, you are doing IDE will just turn on one of the pin, but this one that I just finished writing now will turn all the pin on once. So this one will be able to write into the 8 data buses. The second one, put A equals to 0 times FF. Of course, it's an hexadecimal thing. You will discover this as we go. We'll be seeing these hexadecimal, binary numbers, and decimal numbers as we make progress. So the very first one, take an advantage of one communication, while the second one take an advantage of 8 communication at the same time. The difference there is that the second system is far more efficient than the first system. Sure, you understand now? Because architecture is more clearer at these particular ones, and it's not more clearer at these particular ones. So that is what we mean by it will help you to be able to write a better code. It will help you to be able to do the process better than just when you don't understand anything about the architecture. So if that has been explained, then I could just move into two-stage pipeline. Two-stage pipeline. Now, since we discovered that it takes 2 stages, so pipelining is a method of accumulating, storing, and execution of instructions on microcontroller units. So we are trying to develop a means of, can we speed up this microcontroller? Can we get something done as fast as possible? Of course, if the word pipeline, if we are just looking at the word pipeline, basically, we will have known that it means that you line 2 things together. You want to do 2 things simultaneously. Something is lining against something, pipelining. You channel something at a certain way. So that's what it simply means. So let's look at this slide that explains pipeline. So again, the three processes is being said here. So on this line, you see the processes. On this line downward, you see the numbers of cycles. Of course, this what you are seeing here is numbers of cycles. And again, where is this number of cycle coming from? Please, let's get this all together once and for all, so that we are together and we get it right. This number of cycles is coming from crystal oscillator, because we are still going to get there tonight very, very soon. It's coming from, so if you have 1 mega as a crystal oscillator connected to your microcontroller, that means this 1 megahertz is sending 1 million cycles per second. Because I believe this is clear. So that's 0, T1, T2, T3, T4 that is being shown on my it's been showing on my this stuff is actually I've been showing on my on that axis, on the x-axis, is representing each instruction cycle that has been sent to the microcontroller. All right, no challenge. Let's move. So if my face is not showing, I'm just trying to manage things here. Okay, so that's where T1, T0, T2 is coming from. So if you look at this table in front of us now, it means that at the very first cycle that I receive, I want to fetch instruction 1. Then at the second cycle, I want to execute instruction 1 for non-pipelining cases. If I'm not doing pipelining now, I want to execute that instructions. Then the next cycle, I want to fetch instruction 2. Then I want to execute instruction 2 and fetch instruction 3 and execute instruction 3. Now, if I'm running pipelining, the very first stage, I will fetch first instructions. Then the second stage, I will execute instruction 1, both simultaneously. Can you see where architecture is giving me advantage? Simultaneously, since I'm not sharing the same data buses, I could also load instructions. I could also fetch instructions for the next cycle, instruction 2, and save it while I execute it. You will still see that when I get to the data sheet, I will show you the buses on the data sheet as we go on in this class. So in this class discussing instructions. So then fetch instruction 2, execute instruction 2, fetch instruction 3, and execute instruction 3. Now, what does this do to us? If we just look at the cycle, it is so obvious that in 6 instruction cycle, I execute 5 instructions when I'm doing 2-stage pipelining. And this 2-stage pipelining is the technology that was being imputed into AVR architectures, and even PIC also use this 2-stage. Now, that makes the execution more faster than just when you're not running pipelining. So 2-stage pipelining was used for ATMEGA 32 and also was used for PIC. And I will also show us from the data sheet. Okay, so I believe this the concept of 2-stage pipelining is clear. So so we move to the next thing. Latency. Also, what is latency? Latency is the time taken for the first instructions to be executed. Latency is the time taken for the first instructions to be executed. So of course, it takes 2 instruction cycles for 1 instructions to be executed. So we said the latency of this microcontroller is 2. The latency of 2 stages is 2. Now, another concept that is very, very important is something called throughput. When I will return us back to the datasheet and I will show us where they write all this information, so that you see that we are in line. We are just setting the ball rolling as we make progress. So throughput is the number of instructions executed per unit time. Is the number of instructions executed by unit time. So let's just run through these calculations all together. So if I have a frequency of my clock to be 1 megahertz, which I just talked about now, then that will give me 1 million clock per seconds. For 2-stage, the number of instructions per cycle is 1. So let's look at it again. So in 2-stage pipeline, it means that I'm only wasting one cycle, please. So I'm only wasting the first cycle. The rest, I execute instructions in all those cycles. So what does that simply mean is that approximately every cycle, every clock cycle, I'm executing one instructions. So what does that simply mean? It means that I'm going to execute 1 million instructions in 1 second. If I'm doing 2 stage, then the throughput, my throughput is 1 million instructions per second, which is also the same thing as 1 MIPS, 1 MIPS. So if I'm running my microcontroller at 8 megahertz, that means I will be on 8 MPIs. Then the throughput of my system is 1 MPIs per MHz, mega frequency. All right. So let's look at the datasheet and see these informations being expressly stated for all our microcontrollers. So I stop sharing this, please. I believe it's clear. Latency, the concept of latency, the concept of two-stage pipelining, and the concept of throughput. If I have a questions, I will answer to them. Okay, so I'm sharing data sheets now. Data sheets, come out. All right. Why do I need to? Why do I need to read the datasheet of any project, of any component I'm going to use? One, datasheets contain all the informations that you need to know about maybe the processor or the component in questions. So for an embedded system engineer, it is like our lifeline. So if you permit me to use that, it's like our lifeline that told us what to do and what not to do. You understand? So reading datasheet for a micro embedded person is super important. It's something we cannot just overemphasize, because everything you need to know about that microcontroller is expressly stated in that stuff. All right, so if you follow the way we have been doing before, you have discovered that when we started, I explained each pins and each port, and you find the definition of each pin. This is my screen showing.
Yeah.
So if you observe that, the next thing I did was I did pin descriptions, and which is, I think, last 2 or last 3 class when I was explaining what each pin means. So that was what you find. Then the next thing I talked about the data retention capability features of this system. Of course, this is about C compilers, which is something we discussed in brief yesterday. Then the next thing they want to talk about is the architecture of your microcontroller. You see that I'm systematically actually following the datasheet in one way. You understand? Especially the preliminary sections of the datasheet. So I'm systematically following it. So it was also written in such a way that we could understand it in that way. We could just go through the datasheet in that way. So that's what I am doing here. So these sections of ATMEGA, AVR core architecture in general, the main purpose of this CPU is to ensure the correct program execution. Can you see? To ensure correct programming, the CPU must therefore be able to access memories, perform calculations, control peripherals, and undo interrupts. Of course. Now, I'm going to use this diagram now to explain what we call Harvard architecture in recent. Then look at it. So these are the 2 8-bit data bus, 1 and the 2. 1, this line, this thick line. Let me see if I can zoom my screen. Control plus. Can I get it done? Okay, negative then. So these thick 2 lines are my what? Are my data buses. You can see it, and it's 8-bit. It's 8-bit. So everything within here now. I don't know if I can even have something like a pen that we use. Okay, I think it's here. Yeah. So everything that is here now, sorry, that I circled here now is my program memory. So instructions are fed into program counter. Instruction are stored in flash memory here. Then program counter counts the instructions, know the next instructions to be executed. Instructions were loaded into instruction registers, then instruction decoders, then control lines, which talked about something that should be done. Now this line, let me see if I can change my color. Yes, I could change that. This unit now, these sections that goes down now is my data memory. So under my data memory, I have status and control, then the 32 by 8 general purpose registers. The aim of here now is not to actually do something we called memory calculations, which I believe maybe in our next class I will do the memory calculations. Don't bother yourself that we are doing a lot of this. It's just for the betterment of ourselves and not just so. This is what we talked about, memory analysis, when you begin to look at what will be the starting address of these particular instructions. And of course, here you can see two-stage pipeline also being explained here, how this happens. So when we start looking at those memories in view, this particular symbol is a memory map of a program memory. So program memory map, this is how the program memory map. This is the starting address and this is the ending address. When we get to maybe in our next class, which is tomorrow, I'll be doing mathematical calculations around this place, why we have this application flash memory and why we have this boot flash memory. And this is what Arduino rests upon. That's why I need to explain this very, very well. So Arduino take advantage of boot flash sections so that you can just upload code by itself. So these are just calculations around memories and around EEPROM. So basically I'm following what is in this data sheet. Then once I set everything that I need to set up, which is clock registers, also clock selections. Once I'm done with that clock selection, then the next thing we'll start doing is to start writing code, which I will see. This is the clock distributions, all the clock in AVR microcontrollers, a clock control units. Once I explain this thing tomorrow, which I will try and see if I can combine everything I need to talk about, so that after tomorrow we can get everything running from there. So once I'm done with that basic stuff, we are done with setting everything ready. Once we finish clock analysis, then we can get our microcontroller running. The only one thing, okay, the two things you need to put for your microcontroller to actually work is power and clock. Power and clock. If those two things are ready, then your microcontroller is going to run your code. Yeah. So you need power and clock to get it run. So back to where we were before. So you can see separate data bus accessing this, then separate data bus accessing this. In real sense, you don't have access to program memory directly. So you can either use SPI unit, use interrupt unit. These are now everything that is here now. They were the way we can interact with our microcontroller. We that were in the outside world. So we talk directly to the data memory, the data memory, why microcontroller talks to its program memory directly. So this is an example of Harvard architecture. Now let me just read this straight up to us. In order to maximize performance and parallelism, AVR uses Harvard architecture. Yes, please ask. I'm with you. Hello. Hello.
Hello.
Yes, you said you have a question. Hello. Hello. Can you hear him? Can you hear her, please?
No, we can't hear you anymore. It's for me.
Can you hear me now? Wow. Okay, I can see that now. Check. Oh shit. Hello, can you hear me? Check. Okay.
Hello, Isaac, can you hear us now?
Yes, I can hear you now. Sorry. Um.
Have you been talking? Because we're
Yes,
not
I
hearing
have
you.
been. I have been, but I can hear the time you raised an observation that my network is out, so I stopped talking at that junction. Okay, please ask your question. At that junction
Okay.
where you say you have a question to ask.
Yeah. So I want to ask, the data memory you mentioned, is it the same thing as working registers? Like the one you
Yes.
circled in red at the middle?
Yes, it's the same thing as the working registers. So it is the major registers that the processor might manipulate. So you understand now. So sometimes the easiest way I could also tell you this is that I'm going to put about 3 examples of this. Now the literal pins here, the pins of the microcontrollers, they were connected to these working registers. So you understand now? They were connected to these working registers. Let me see if I can show you something. I believe it should be there. Let me see if I can show you something. So it's very good. I want us to ask questions. That's just the truth. I want us to ask questions so that it will also take me to be able to explain much more deeper than just being on surface. Do you understand? Let me run. I want to show
So can
you.
you increase the can you zoom your this thing a bit? Like that plus sign that's at,
Yes.
can you press on that plus
Yes,
sign?
I've
Just to
pressed.
increase it a little bit so that
Is it bigger now?
yeah. Yes, fine. Yeah, that's done.
Okay, so I'm running to a very better place to give you an example of this. I've answered your question, but I want to put more uh source to it so that it's fine. Okay, brand and detections. I don't need to explain this now. I'm just trying to even let me search for it. Port A. Port A. No, this should be fine. Port A registers. Okay. Just looking for something. Sorry. What happens here is that, even as I look for this, what happened here is that if okay, let's go to home so that I don't even waste our time. Now, what happens here is that look at port A registers, for example. You see everything on this port A now is connected to a working register called general purpose register. You understand? Port A general. So this is a general purpose register. So if I affect what is happening in this register from the CPU end, you understand now? We don't have access to this. If I affect what is happening to this register here, the effect happens to this pin. For example, if I write 1 0 1 1 1 and 1 and 1 and 1 here, what will happen to this place is that the register will update this place and you find 1 here, you find 0 here. You understand? You find 1 here, you find 1 here. So it is the working register now that you are talking to. Did you get it now? So
Yeah.
This is now the working register. Now, but I need to make one explanation why I want to do this is this. Because I say port A register is connected, and I say port all the pins of pin A is connected to port A register, it doesn't mean that certain time this port is being multiplexed, these pins are being multiplexed. Now, I explained something at the beginning of this class that if you use it as a general purpose, you can use this pin A to this and you'll be talking to port A registers. But certain time you'll be using them as what? Analog to digital conversion. In that time, when you are setting up this thing, you will have disconnect this from port A register to ADC0, another register. Did you get it now? That processor can still work on that register. Okay. Did this explanation, did it go well, or I should do it again?
Yeah, you should again.
Let me explain it again. The fact that I said that there's a working register for port A called Trace A register and port A registers, or sometimes if you are looking at ATMEGA, for example, we call it DDRA and port A registers. I will still explain that in details. But what I'm saying is that certain situations when I don't want to use port A as a general purpose pin, but I want to use it as an analog to digital conversion. You understand? So it's like you take a switch internally. Please try and understand this concept. It's like you take a switch internally, and instead of switching port A to all this pin A now, let's say pin 40, instead of switching pin 40 to port A register up, can you see my hand? You decided to switch it to another register called ADC. So at that time, even if you write something to port A here, it doesn't do any function. Whatsoever is in port A register now cannot affect this pin now, but it can affect this. So did you get it now?
Yeah.
So I can also still do it this way. So I can also still do it this way. I can also still do it this way. Let me take my pen. So this is pin 40, for example. So this pin 40 now has a switch. Can you see? So you see that you connect it to port A register. You understand? Let's call this RA, port A register. Or you connect it to ADC. Sure, you understand now? Now, whether it is ADC register you are talking about or port A register, these two registers are working register for your CPU. Sure, you get now? So invariably, whatsoever happens to here can be transmitted to your pin 40. So they were all working registers. You understand? That your CPU can manipulate at any point in time. Is that clear enough?
Yeah. Well, you mentioned multiplexing. What's that?
Okay, multiplexing is a system in electronics when you try to make one pin, one particular GPIO to do like 3 functions. So it's like you switch on something for this. This same me now, for example, you understand now? I can say I'm a pastor, I'm an engineer, you understand? And maybe I'm also doing something. So if you meet me maybe on Sunday morning, I'm acting like a pastor. You understand? If you meet me on Monday morning, you meet an engineer. You understand? If you meet me on Saturday, I train students on coding, on STEM, you meet a secondary school teacher. Sure, you understand now? So myself are being multiplied in 3 rows. Sure, you get now? So you see that I'm acting like this based on the time you met me. So that's what multiplexing means. Is a technology you use, maybe along the line also. It's a technology you use when you run out of GPIO pins. You know, if we really want to say, are you with me, man? If we really want to say that we don't want to multiplex pin, that means each microcontroller will have plenty pins. Did you get me now? If we say we just want this PA0 to act as PA0 to PA7 without doing any other addition, that means, and we still need analog, that means this is already 48 pin. Did you get it now? So if we straight out this also, that means we are already at 56 pin. Did you get it now? If we set out this one, that means we are already at 64 pins. If we don't multiply it, maybe each microcontroller will now has 80 pins, which doesn't make sense. So we want to save that number of pins, because the bigger it is, then the cost of manufacturing also. Sure, you understand now? But with that, and if you have heard about something called FPGA before, if you have heard about feed gate programming array, if you have heard something about FPGA, you discover that they have so many pins, plenty pins. It's because they want to make the result in real time. So in that way, you will not be waiting for, okay, let me still say this along the line. In runtime, you'll be hearing this frequently when we start writing code. Something in runtime, not in runtime. That means when the microcontroller is working, that's what we mean by in runtime. You can actually change this pin again. It says along the line, stop doing ADC conversion now. I want you to act as a digital pin now. You understand now? So along the line, you can also change it in runtime. There are things you can change in runtime. There are things you cannot change in runtime. That is the explanation. So that registers now that is behind this pin, that this pin is connected to, is what we say the working register for our microcontroller. It is as clear as that. I believe it's clear now. Is it very, very clear now? Auntie Uche?
Yeah, so yeah, it's clear. So how do you change the function of each pin, like from GPIO to ADC, using the code that you write, right?
Yes, it's in the code that I write. Yes, it's in the code that I write. For example, let me just write something simple like that. So if you write, let's say we're in PIC now. If you write answer A equals to 010001110. For example, that's, let me calculate, 1 2 3 4. Yeah. If you write this, it means that pin, the very first pin A0 here, make it digital. The next one make it analog. The next one make it analog. The next one make it digital. The next one make it analog. Okay, I've not sent it, sorry. The first one make it digital. That's what that 0 means. Answer register is the one that activates whether a pin is going to be analog or a digital pin. You understand? You are now seeing that. So in runtime now, so this one will make the first pin. This is pin 40. You understand? Make it a digital pin. Make the next pin an analog pin. Make the next pin an analog pin. Make the next one a digital pin. Maybe you finish your analog to digital conversion and you run out. You still want to do digital. Then you come back again. You say answer A equal to 0 multiplied by FF. Then this one will make everything analog. So it means that in runtime you can actually change it. But you know that the implication of this again is that your circuitry must be able to sustain this. I don't know if you understand. If you can do a circuitry that can sustain this, then you can do it. You can do it in runtime. That means I just disconnect it from digital output to analog input, and I can keep changing that in runtime, and it's going to work.
And analog is the GPIO part, right?
Analog is not the GPIO part, it's the digital that is GPIO part, which is the next sections. We are starting with our GPIO programming. Almost.
But you say ADC, analog to digital converter. So what is ADC for?
Okay. Now let's look at it in this now.
Sorry, so I was
no problem. You are free. You are free. That's why. I'm not offended by any questions. That's just, even if I did not know it, I will tell you I didn't know, and I will go for research. That's just the truth. And also let me share this with us. The reason why I prioritize training, I prioritize teaching people, because it gets me better. That's from my own experience. I become much more better because I don't wish to run away from challenges. So if there's something we don't know, I have people ahead of me also that I'm also connected to, as I told you, that okay, there's this question, please put an answer to it. But before we get to that question, things don't go far. All right, so I'm showing us a nice what I'm drawing now. So let's call this IC LM35. So LM35 has VCC, or something I can call VCC positive, and yes, analog output A0. Then you also have ground negative. You understand now? So if I'm teaching something here very I consider very critical, look at this graph. This is a graph of millivolts against temperature for this sensor, and the slope of this graph is such a way that that's M. The slope of the graph is M, in such a way that you have millivolts over temperature. And the slope, I guess, is, if we go this way, it should be 1 over 9.8. So that should be millivolts divided by temperature. Now basically, an analog signal is that signal that keeps changing in real time. As the temperature is changing, you understand, the signal is also changing like that, you understand, in millivolts. But digital signals are the one that is just maybe high or low or high only. You get it now? So if we said that a pin is an analog pin, like you can read an analog is an ADC pin, that means if you send this kind of voltage to it, it's going to interpret it and give you the digital equivalent of this value. You understand now? It's going to give you the digital equivalent. Let me clean everything. Clean. So it's going to give you digital equivalent of that circuit. But when you say a pin is digital, that means it can only give you high or low. You understand now? So this is it. So you have a voltage like this that is coming like this. So by the time you put this into ADC, this value now, ADC will give you the corresponding value in digital of that pin, so that your processor cannot work with this value, but your processor will work with the digital equivalent of this. You get now? So that is like you are using ADC. I'm still going to put numbers into this so that I can put perspective into this. So let's say 33. Let's say what it gives me is 33 millivolts. 33 millivolts. So when you feed it 33 millivolts into ADC will give you 8. Let's use 8-bit ADC. ADC will give you 1 0 0 0 0 0 1. I believe that should be 1 2 3 4 5 6 7 and 8. So this is actually 33. So this is what ADC will convert what your 33 millivolt that you send into it to. Then this value will be picked by the processor, and the processor will use this value to make decision. You get now? Now it's different from when you are saying that this kind of value is what is coming directly to your microcontroller. That is when you configure this microcontroller as a digital GPIO pins. You understand? That's just the two difference between when you have a pin as analog and you have a pin as digital. We're still going to do plenty of it along the line this class, but since the question that was asked, then I need to provide an answer to that. So that's what it means. So a pin can act as a digital today, but can act as an analog tomorrow, still in the same program, but this pin must have the capability to multiplex with that function. I explained that at the beginning of this class. It's not all pins that can do analog to digital conversion. Even from the data sheet, you saw that there is only port 8 that can do that. I don't know if that is clear.
Yeah, I got the part of ADC.
Okay.
So, how does the input to GPIO pin, how does it look like?
It looks like high or low, on or off.
Okay.
Should you get now? It's not actually changing with that. So, where are we? So, at that junction, I'm saying I'm just following the data sheet to bring perspective to all this. Okay. So that has been done. Okay. I'm at that graph. This is where we are actually. So this is the program memory, and this is the data memory, and this is me outside the world. This is me outside the world interacting. So I can interact with this microcontroller using something called interrupt units. I can interact with this microcontroller using something called SPI unit. I can interrupt through this microcontroller using something called watchdog timer. I can interact with this microcontroller called analog comparator, IO module 1, IO module 2, IO module 3 to IO module N. Interrupt unit, I've explained what interrupt is. We are going to feed in programs to our microcontroller using SPI unit. Now, peradventure, microcontroller has ability to reset itself if the program runs into an error along the line. That is what watchdog timer does. It watches if the whole process is going the way it should go. If it doesn't go the way it should go, watchdog timer try to interrupt and reset your program itself. So we can also interact with this using analog comparators, which I believe as time goes on. So I said I want to read this statement. That was where you actually bringing the question. In order to maximize performance and parallelism, that is not a new story again now. The AVR architecture uses ARFAD architecture. The AVR microcontroller, that's half vegan risk reduction and risk instruction set microcontroller, uses ARFAD architecture with separate memories and buses for program and data. Can you see? For programs and for data. It's a two separate buses, and this is the buses. This one is for program, is for data, and this one is for program. Alright. So instructions in the program memory are executed with single level pipelining. While instruction is being executed, the next instruction is being prefetched from the program memory. This concept enables the instructions to be executed in every clock cycle. I believe I've explained this. I believe this is clear in this class.
That's two-stage.
That's two-stage pipeline. Yeah. Now, let me also say this as an addition. Current CPU are super fast, and the current CPU are actually ARMS microcontrollers, ARMS CPUs. They were the one used in 3D printers. They were the one used in those embedded systems you find in more reward now. They were actually ARMS microcontrollers. Note that they were 32 bits. They are all 32-bit systems. They were not 8-bit systems. And then again, they use, some of them even use 6-stage pipeline to just ensure that these guys are super fast. Program memory is in serial reprogrammable flash memory, which I explained that a bit, but that we dealt with that so much in this class. How did I fit programming? The fast access register files contain 32 times 8-bit general purpose working registers. Let me explain this statement because I find it's interesting. The name ATMEGA 32, that 32 comes from this word, and that's why I want to explain it. That the fast access registers file that you are asking me, which is a GPIO register file, is 32 kilobytes, and that 32 kilobytes are 8-bit each of them, and this is the general purpose working register of questions. So in our next class, which is tomorrow, we'll label these registers and we'll look at a point, can I get to a point where I cannot access these registers again, and how will I write my code to access these registers? I'm going to talk about them yesterday, tomorrow, so that 6 of these 32 bits, 32 working registers can be used, and there are 16 bits indirect address register. Don't worry, when we get there tomorrow, I will explain this. Why pointers have to come in, register pointers have to come in, and why we have 16 bits instead of being able to access all these things. That if you have 16 bits, so I just use this to explain. And the program memory is divided, so we are like going into memory sections now. The program memory is divided into 2 sections: the boot program memory sections and the application program. So everything we are going to be writing as our code, which is called application program, is going to stay at this junction. Why this is, as you start up, what you start up with. And both sections have been dedicated by log bit to write them. So I'll explain something about log bit at the beginning of this class. It's coming again tomorrow when we're going to look into this now. All right. So let me check what our schedule looks like today. Then if there's something else I've not captured, so I can quickly look into it. So our schedule today says that why we need to understand microcontroller architecture, 2 types of architecture, why alpha architecture dominates computer and microcontroller world, 2-stage pipelining, concept of latency, throughput, and frequency, then introduction to datasheet and the importance of datasheet, evaluating 16F877 and ATMEGA 32 microcontroller. All right, let me quickly look into something as we come to the end of this. Let us not go there first. So I want to just show us something. Okay. Okay, this is what I want to write. Overview of this microcontroller. And now I'll try and open PIC datasheet, at least for this class also. Let us just scan through it and see some similarity and difference that okay. ATMEGA AVR ATMEGA. The ATME ATMEGA 32 is a low power CMOS 8-bit microcontroller based on AVR enhanced reduced instruction set architecture. By executing powerful instructions in a single clock cycle, so it can execute in one single instruction cycle because it's 2-stage pipeline. We achieve a throughput. I explained the concept of throughput. Approaching. Why is it approaching? I believe we should understand that from this class. 1 million instructions per second per every megahertz that you use, allowing the system designer to optimize power consumptions versus processing speed. So I believe from this datasheet now, from here to here to here to here to here to here, I've explained everything that is there. Everything that is there to this junction. Everything that is there. Alright. So let me see if I have downloaded this datasheet. So open this up. So I'm opening PIC 16F877 datasheet. So once it shows, my screen is still showing previous information, Abby. Yes, let me just share the PIC screen now. Okay. Peace is not even here again. Alright, so we have now microchip. In the other hand, they have so many products. So what they do is that they tend to code it. So a datasheet cannot be developed for all the families. So we have PIC 16F87XA series. So in that series, we can find a 28-pin microcontroller, 40-pin microcontroller, and 44-pin microcontroller, all enhanced by flash memory microcontrollers. Of course, that is not a new thing to behold again. So in this datasheet, you can find this datasheet relevant for 4 devices, which is PIC 16F8 873, 874, 876, and 877. So of course you see only 35 single instructions you need to learn, provided you are writing in assembly language, but you don't need to learn that one if you are writing in what, in C. All are single cycle instruction except for program batches, which are 2 cycles. These are also talking about two-stage pipelining, that every instructions can be executed within one instruction cycle, except some programs, some instructions that will involve you to do 2 cycles. Like if conditional statements are going to run 2 cycles, there's no way you can do it. So operating speed, it means that this guy can use, if you look at ATMEGA 32, I don't know the maximum speed, but let's just look at it once and for all and see. So what we are doing in this class now is, at this junction, is to try and see the difference between them, the 2 microcontrollers, and so you can see this guy can run maximum speed of 16 megahertz. Can you see? Why this guy can run to 20? Can you see? This guy can run up to 20, so it's faster than ATMEGA 32 in one way or the other. It's 18 kilobytes by 14 word flash memory, so it's 8 kilobyte flash memory. Why this guy is, let's see this guy flash memory. I believe it should be here also. It should be here. Okay, flash memory. This guy is 32 kilobytes. This guy is 8. It talks about the number of instructions, the number of code I can write, and the flash memory will get exhausted. So this guy data memory is 368 bytes by 8 bytes. That's his RAM. So let's look at this guy's static RAM. This guy's static RAM is 2 kilobytes. Far better than. But this guy has a speed that this guy does not have. That's the only thing. So you can also see the EEPROM. The EEPROM is 256 bytes. Why EEPROM of this one is, of course, 1024, about 1 kilobyte. So ATMEGA is better in memory but lower speed, while PIC is better in speed but lower memory. So then, of course, this guy has timer 0, timer 1. Okay.
Sorry, ATMEGA is better in memory.
Yes, it's better. But lower speed.
Why PIC?
It's better in speed but lower memories. For the 2 microcontroller we are considering for this class, you understand? Doesn't mean that you will not see PICs that is better than this ATMEGA in the market. You understand? So for the 2 ones that we are using in this class, we are using, for the purpose of this class, we are using 877A, PIC 16F 877A, and we are using ATMEGA 32 for the purpose of this class. So I'm comparing those 2 products side by side. So not really all. So timer 0, timer 1, timer 2, let's quickly look at it. Timer 0 is 8 bits, timer 1 is 16 bits, and timer 2 is, you can see that one thing you will see again is that the data sheet of PIC tends to be more robust than data sheet of ATMEGA. Let me show you something. He said it's 8-bit timer or counter with 8-bit prescaler. I explain what prescaler here is, and don't worry if it's not still clear. It's a divider that divides the main time by 8 bits. So you can divide this 20 by 8 and have that timer runs here, so that your timer doesn't run out of 8. So let me do the math. No need to. So if you do 20, if you do 20 divided by 8, what does that one give me? That's 4 here to 4 here, 5 by 2, that's 2.5, I believe so. That's 2.5. That's 2.5 megahertz for one cycle. So for one cycle of this, you can count 2.5. So before you run out of 8, This might be looking too much. We are just comparing them. Timer 0, 8-bit, timer 1, 16-bit. What is important to me now is that they specify the prescaler and give me everything. They said this with prescaler and can also be incremented during sleep via external clock. I explained something about external clock. If you remember, there is a pin here. There's a pin here when I was trying to explain this pin. That this pin can be used to provide clock, external clock for a timer, for timer 0. That you can provide external clock for timer 0 using this pin and timer 1 using this pin. That's what they are trying to talk about here. Timer 2 is 8-bit. So this guy has 3 timer. Abi, this guy also has 3 timer. This guy also has 3 timer. 2 8-bit timer and counter with separate prescaler and compare mode, and 1 16-bit. So on timer level, they are same. You understand? On timer level, they are same. Both of them has 2 8-bit and 1 16-bit timer. 2 capture compare PWM mode. This capture compare can work in 16-bit, 16-bit, and PWM mass resolutions of 10-bit. I guess ATMEGA does not have PWM out. Okay, he has 4 PWM channel. That's fine. So they are also on the same level here. So synchronous SPI mode, I2C, but they both have the same thing. 9-bit address detections, they both have the same thing. Brownout detections, and you find.
What is I2C store? I2C.
Okay, I2C is inter-integrated circuit. Inter-integrated circuit is a form of communications that is synchronized serial communications. Synchronized serial communications. I will try my best if we can even do that in this class. You understand? It's towards communications in. Let me explain it, at least just for now. So we do communications in electronics because we want to save GPIO pins. Let's say, let me share a theory, and I can also browse this to verify this. Your USB of your computer, the USB of your system, of your laptop now, can take 999 devices. One USB can take. That means you put flash, you put USB, or you keep putting flash, That one USB port can take 999, if I still remember what IEEE is saying. But these devices must not be far than 5 meters from your laptop. So if you put 999 USB, then it means that instead of you to imagine this, man, that if you want to actually build a computer like that, that means everywhere around the computer is just USB port. Did you get it now? But one USB port can support that kind of communication. What did you do? You reduce the GPIO ports, the pins that the port that you need. You just reduce it by using. So I2C is like one communication procedure. You understand? Like USB. This is USB. Universal Synchronous Receive and Transfer Communication. This is USB. Yeah. Why I2C also stands. So I2C also adds the maximum number of devices it can support. But USB uses 4-wire. I2C also uses 4-wire. But in USB, it was asynchronous. But in I2C, it was synchronous. What does that simply mean? In USB, you don't set timing for them for the communications. Asynchronous means that there is no timing for them. Synchronous means that the master set timing for all of them. Let's just leave it like that now. When we get to, I believe I'm going to do something serial communications immediately after we do interrupt. The next thing we are looking at is serial communications in details. It's something that is more that I cannot quickly compress everything. Sure, you get me? So that's that. So brownout detections, and you find out everything about this. Has 100,000 erase and write chances. For flash memory. Let's look at this. What does this give us? I think we read that last time. We read this in one place last time. Okay, 10,000. 10,000 for flash and 100,000 for EEPROM. Can you see? This is 10,000 for flash and 100,000 for EEPROM. Here they said 100,000 for flash and 1 million for EEPROM. That means in rewritable things, just like PIC is better. PIC is better in flash memory than this. So, of course, should I need to run through all these pins? Okay. So
Yes, me too.
all right. So let's do the comparison of our targeted. This is our targeted microcontroller. So these are our targeted microcontroller. Let's run this as fast as we can. Okay. This is port B. You can see different from this.
Can you please document a bit?
I will do that. Yeah, this is port A that is on pin 40. Yeah, but when we come to this one, it's port B. Can you see? It's port B that is here, but that doesn't change anything. So you have port B up here. So I'm going to be taking them one by one. So RB0 to RB7 is just a normal GPIO pins. Now, this RB0 is being multiplied with external interrupt pins. So you can supply external interrupts to this pin. That's what this pin does. I explained interrupt at the other time, and I'm going to talk about it also very, very fast. What is interrupt? Let's say as we are discussing like this now, maybe you just observe that the call coming, you just quickly pick that call. That's an interrupt. You stop the process of what we are doing, then we quickly go and attend to that interrupt and return back. You understand? So what did we call external interrupt? Interrupt actually had, as we're going to be looking at it in details in future. After GPIO pins in this class, the next thing we want to talk about is interrupt. So now there are internal interrupt, there are external interrupt. So this is an external interrupt. This interrupt can be classified, can be configured, maybe rising edge or falling edge. Maybe this guy just see a high. Let's say you create an emergency button, and that emergency button is connected to VCC. Once you press it, that's the rising edge. It will just trigger an interrupt. Maybe emergency stop, something that just happened. And I did this in my inverter code. Maybe later in the day I will explain that. So that is interrupt. So this is PGC and PGD and PGM. They are the pins for you to program your microcontroller. I talked about the programmer used for PIC is PIC Kit 3. I believe I've talked about that in this class also. Maybe I should just show how PIC Kit 3 looks like. I'm online already, so I can do this. PIC Kit 3. So there's something, okay. PIC Kit 3 image. I think there was a time I want to give me pin out. So this is how it looks like. So can you see that you see PGM, PGC and PGD? Can you see? PGM, PGC and PGD. These are the pins that comes out of your PIC-K3, the programmer. You understand? So they goes into this pin for programming. And if you find is the data, is the clock, and is the mode. So that's the 3 pins. Yes, is it yesterday I was explaining something about PIC, that program on go. I think I talked about something like that. That there's something that is possible with PIC programmer, that you don't need to keep going back to your software. When I was explaining something on MP Lab, that if you put your program in that mode, you just keep pressing this button, connect the new microcontroller, press this button, connect the new microcontroller, press this button, and it will just be flashing the same code. You understand? Instead of you going back to MP Lab and
That was on batch
MP
something.
Lab ID
Batch.
yesterday. I was explaining this on MP Lab ID yesterday. So this is what I mean by that. That's the button I say it will be on the programmer that you just have to click on. I'm not in the office. I will have shown you this programmer in real sense, like in real life in my hand here. So it's part of the list I actually sent along the line. So no. So let me go to port C. OCS1 and OCS2. They were crystal oscillator 1 and crystal oscillator 2. Similarly, these are the pins at which you connect your crystal oscillator. So these are clock outputs 1 and clock inputs. Let's run through it. Clock selection bit. So I can make this. I will make this interesting. Okay, I think this actually also make this better. It makes the data memory, data buses much more better than program counter that we did previously. It makes it more better. This okay. So let me use this pin. Let me use this table to just do the pin out so that it's clear. And OCS1 or clock input 1 is on pin 9 if you are using SOIC. Of course, I explained this PDPI, which is dual inline package. You're using this kind of package QFN. These are the pin number at which it is. Or crystal, oscillator crystal, or an external clock input. That's what this pin does. Oscillator crystal input or external clock input or Smith trigger buffer when configured as RC mode, otherwise CMOS, external clock source input. Please, these are questions coming from clock sources, and for PIC microcontroller, it has about 6 clock sources, same as ATMEGA 32. So that should be, if not tomorrow class, if we cannot get there tomorrow, we'll be able to get there next tomorrow. But let me put next class. But let me put a simple perspective to this. You know, I said that there are 2 things microcontroller needs to work: the power supply and the clock. This clock can be given in different modes. One of the modes is internal RC. So some microcontroller has internal clock. You understand that even if you don't have external crystal oscillator to connect to them, you can use internal crystal oscillator. Now it's not only crystal oscillator that can provide this timing. So resistor, the series connections of resistors and capacitor will give you the same timing. This is basic electronics now that I did not touch that time. Let me quickly do that. So if you have resistor like this, then you have a capacitor like this, connected to ground this way. Then this output EMA is also an oscillator. It's called RC oscillator. How does it work? Let's do it fast. It works in this simple principle. So you know that this is our capacitor. This is charging curve of a capacitor. It charge full. Then resistor comes in, discharge it. Can you see? Then capacitor charge full again. Resistor comes in, discharge it. Then capacitor charge full again. Resistor. Later in the day, you find that on and off cycling. Can you see? That you need to power your microcontroller. To tell your microcontroller, you remember that if it is 1 megahertz, it's sending this on and off for that megahertz. Of course, this is not as perfect as crystal oscillator. Now, there is also something called internal RC circuit that was built inside the microcontroller itself. You can decide to use that mode. So this explanation is coming from, if you have an oscillator crystal oscillator that is external, this is where you connect it to. Or you have an external clock input, which is RC, connect it there. Or you have external clock sources, you connect it there. That's what it means. Did you get it now? At least on the basic level, when we are doing cloud sources, we're still going to revisit this. So this also is the cloud sources. This pin is master clear and it's actively low. Master clear is also the same thing as reset buttons. Master clear input is and programming voltage output. Okay. As we move on, I will be putting more details to this. It's going to be a lot of stories. So this is a port A, and port A is a bi-directional. Can you see? It's a bi-directional port. It's either you connect it to a digital or you connect it to an analog. Can you see? That was what I was explaining before, that it can be connected as digital or as an analog. So you can find all this, what all these jargons actually means were analog to digital conversion. That's why I can explain it also into details. Now, what does, for example, RA1 is a port A. Look at this line. If you follow this line like this, it means that it's an IO port, input or output port. If you are using it as RA1 and it's a digital. If you are using it as an analog, then you convert it also AN1, analog input 1. You understand? For this one, I talked about reference voltage. This is where you can give reference voltage, ADC reference voltage low. So this comparator, I talked about something you are comparing two voltages, and you can use the same pin for it. All these ones is in output mode, input mode, input mode. You understand? If you are using analog, it's going to work as an input. If you are using ADC, it's going to work as an input. But if you are using it as a comparator, it's going to work as an output. You understand? This is what each of this pin means, one by one. You can just look into this. But the interesting thing is that almost everything I've explained, low voltage single supply enable pin, that's PGM, PGC, in-circuit serial programming, in-circuit serial programming data, and you can find all the details of what this pin means. It's almost similar to what I've explained before about serial transmission and receive and everything like that. That's that. So I think I could share this again also. Stop sharing and share this again. Let me share my slide again to come to this. Share my slide and present something else. So I want to share my slide. You can share slides. Okay, so that is showing now. If you look at this slide, this is what I was explaining. There's data input, there's data output for JTAG interface. Then this is when I was explaining general purpose input. This is when I explained shifts the master as in master. This I will use for SPI. It's the same thing I explained here that is applicable to the new datasheet. But there's nothing to worry about. Even if you forget something here, when we are dealing with that particular unit, maybe we are dealing with analog to digital conversion, or we are dealing with comparator, we are dealing with this, we are still going to revisit them again in much more details. And as at that time, it's going to make much more frequent sense. What I just did in that day is just something like an overview. And I think with this, I have compared PIC 16F877 with ATMEGA 32. See the one where this one is stronger, where this one is better, where this one is for the purpose of this class. And that I have covered everything I'm supposed to cover in this class. If there is a questions, I'm open. You can ask me questions. The good thing is that this class is also pre-recorded. It's also recording like this, and once I edit everything, which is small editing, I'm going to share the link to our YouTube channel. Then you can get all these classes there. I'm still considering whether to make it free or to make it only people that has link. Even if I'm going to make it some free, some of these classes free, because you paid for this, and value has to also be put on our time and everything. So I might just make few free, and others we just have, if all of us has the link, can only be the ones that can access that stuff. I'm still considering that so strongly. But now we have been recording the class since yesterday. It's just the first week that we did not record the class. Alright, questions, then contributions, your opinion, your view, as we round up tonight.
Yes, good evening, sir.
Evening, sir.
Yeah, yes, that was what I was about to say.
Okay.
About the recording, because today I was just my network was reading. My network really
They came for me and you together.
was really bad, so I couldn't really catch up with what you're saying in class today. So I was even asked, so I want to ask, you said it enough to ask, so I want to ask you, that's, when should they expect the video so that you can just catch up? Because I have a question, but I know that you might have explained one to things that I'll need to know out of the class, so I would love to get the links as soon as possible so I can catch up. So it's not, you're not being too much lag.
Okay, what I will do is that let me make commitment that tomorrow I should be able. Tomorrow is okay. We're already on Sunday. Sunday is a bit busy day for me. You know, we are still having another class this evening today. So, but let's see, because I don't think I have so much editing to do on this. Maybe I will just have to put one small music background and a like introduction, the opening title. I think that's and end capture. That should be all I need to do. So if that is being done, I will just send it. I think I can take Zach to do that for me. You know Zach now. You can just add those two things for me and we'll push it out tomorrow. Don't worry. I will try my best. And the previous class also. We'll push both of them out tomorrow. So that I can't do it today. Alright. Well done.
What time today should I remind you?
Remind me around 4. Around 4. Anytime I'm doing church, I should be done by 3:30 thereabouts. So,
okay. Thank you, sir.
You are welcome.
Thank you, sir. So, when I watch the video, I'll maybe the next class I have a little research questions. So I'm just keeping it.
No challenge.
Maybe I'll get it when I watch when I get it.
Yes, of course. Once you watch the video and you have concern, please, that will be the first thing to be treated tomorrow. I promise.
Yeah, thank you, sir. Well done. Thank you, class.
Auntie Uche.
Yeah, I have another question.
Okay.
So you've explained about you try to compare ATMEGA test and the PIC. So aside from speed and memory, is there any reason why I should choose any of them?
Okay, there are reasons why you should choose any one of them.
Aside speed and memory.
Aside speed and memory. Now, going by first, you see what is more important here is that getting what you want to do without less stress, without so much stress. That is very important to you than even whether you are using PIC or you are using ATMEGA. Anyone that will not stress you so much, I suggest that's one you should use. Because you are looking at 32 kilobytes. That thing is plenty when you start writing your code. You can't even exhaust it. You understand? Even till the end of our class here, we can't exhaust. We can't run out of memory. I think in my whole life, while I've been writing code, I have just run out of memory once when I was doing a PhD work for one engineer in UNM. That's the only time I run out of memory. And you can imagine that code was just plenty lines, plenty. So that's the only time I ran out of memory. So for you, memory is not even a problem. Do you understand what I mean now? Memory is not a problem. Speed is not even a problem. All of them are super fast. Even that 16 megahertz is fast. Now, the question is, why will I want to go for PIC over ATMEGA? The answer for me is PIC had a more supporting environment. You understand? If you Google I have a problem, like just Google the problem, just type the problem on PIC to Google, you have more response. You understand now? Than ATMEGA. 2 reasons. 1, the reason why Microchip even bought ATMEGA the first time is because they have supporting systems. And you can see For example, in this class, we ran MP Lab ID, yes or no, without any issue. Your practice is what the basic thing. But you ran ATMEGA, ATME Studio, we have an issue. Did you see it now?
Yeah.
That is just obvious why you should go for. And I said that for the purpose of this class, I'm also going to be using MP Lab SID, because almost everything that will be a challenge has a solution. That the solution is flying everywhere. If you look at PIC microcontroller datasheet and ATMEGA 32 datasheet, you already see that PIC carry much information than ATMEGA. You understand? The only thing, again, I could also tell you from experience, PIC 16F877 that we are using here is around 3,500. ATMEGA 32 is around 5,000 naira in Nigerian money. Have you seen the difference now? The ATMEGA tends to be much expensive. Cost is also very important. Yesterday's class, I explained something that your engineering solution should meet 5 requirements. 5, functionality. 2, safety. It must be safe for people. It must do what you say it will do. That's the first one. It must be safe for people to use it. It's not that they go and touch that and the thing shock them. Number 3 is that it must be durable. It's not that you buy it today, it spoils tomorrow. Very, very serious one. Number 4 is that it must be artistic. Chinese come with that, and they come with artistic and everything is fine. Everybody go for them. The number 5 thing is that it must be cost effective. In short, if I want to rearrange it, my own arrangement is functionality, safety, economical, then artistic, then durability. For my own classification. So I mean that first of all, consider functionality. 2, consider safety. It must be safe. 3, it must be cheap. Maybe because I'm a Nigerian. If that thing is expensive, your solution is as useful for you and your family alone. Then number 4 thing is what there are some expensive things that you yourself cannot afford for yourself. Number 4 thing is that it must be beautiful. Everybody wants something beautiful. Then 5, it must be durable. I find out that gradually our world is moving from durable products to beautiful products. Yes, our world is generally moving from durable product. That's what China came with. They came with cost effective.
Your network is cut off.
Can you hear me now?
Your network.
Hello, can you hear me now? Hello? 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 Hello, can you hear me now? Hello? This network issue.